This is our second lesson for Unit 5, where we're looking at the question of finding the perfect area under a curve. And last day we were far from perfect. Last day we were doing this rectangular approximation method, where we had these big chunky rectangles, and we were deciding whether we should attach them left or right, and just kind of getting set up for finding nice, beautiful areas, but we were definitely not finding perfect areas. We're going to get closer today. We're going to look at some things called Riemann sums. So Riemann is a person. He's no longer with us, and he came up with this plan for kind of refining the approach for finding the area underneath the curve. So we're going to be looking at these things called definite integrals. We'll get to that, but we're going to start off with some things called Riemann sums. And so when you hear people talk about Riemann sums, this is really just more approximations. They're going to get better though. But more approximations of areas with rectangles. But we're going to lay down the groundwork for getting this to be perfect. Now I've got just a nice little parabola here, and I want to show you kind of the general plan for how Riemann would do this. And then we're going to go and say, okay, well, can we lay this down specific or in general after we've seen this specific story? So I want to try a specific story here with 4 rectangles, just 4 Riemann rectangles, and we're going to do it on the interval from 1 to 13. So imagine you have a need to start at 1, finish at 13, and find the exact area under the graph. Okay, so beginning here and finishing there. And we're going to do it with 4 rectangles. Okay, we're going to go for a walk of 12, and we're going to do it with 4 rectangles. And I want to show you what Riemann would do. And at the beginning, I'm just going to go and just draw some little rectangles in and kind of move them around. So maybe just watch for just a second, right? So just kind of getting set up here. Just want to get my colors right. Okay, we'll fill that in. Maybe make it so it's kind of transparent. That always looks nice. Okay, I'm ready to go, and I'm going to start going ahead and getting ready, getting my tools in place here to go and start approximating this area using some rectangles. And so, you'd think, right, we're going to go from 1 to 13, 12 steps. They've told us, hey, do it with 4 rectangles. Okay, well, if they're 3 each, that'd be great. But here's what Riemann does. Riemann's really casual about this, right? In fact, let me show you some pictures of him here, right? So here's a picture of Riemann, right? There he is, sitting down in a chair, posing for a little photo here. And, he seems pretty casual. He's pretty laid back, right? Just kind of a casual pose. Kind of reminds me of this guy. This is probably like Riemann's, I don't know, nephew or something. Just like, yeah, pretty casual. So I want you to think Riemann is relaxed, right? He's not really upset about how people are doing this. You really can't get him riled up, right? So he's watching you build the fence, and maybe you take this first fence run, and you're thinking, oh, I got to impress Riemann. Maybe I'll make it 3 wide. Oh, geez, where should I attach it? Should I go left side? Should I go middle? Middle's nice. Or should I go right side? And Riemann is like, yeah, whatever, man. Just nail it down. Put up that fence. And he might say, I don't care. Why don't you go and attach that fence right here at that X value? And you're like, are you serious? That's not even the middle or the left or the right. And he's like, yeah, this is relaxed Riemann building. Not a big deal. And he's like, grab another fence run. Let's just slap it up in here. And then he grabs it from me and he's like, here, let me help you out. And he goes and he does this. And you're like, Riemann, what are you doing? That fence run is actually too narrow. And he's like, no, it's fine. And then he goes and he puts a point maybe right there. And then he goes and he grabs the next fence around. He's like, oh, okay, yeah, let's just go and slap this up. Maybe we'll go and make sure it's attached here. And you're like, oh, you mean like on the right side? And he kind of looks at you, right side, what are you talking about? And he goes and he attaches a fence run that looks like that. And you're like, whoa, that one's really fat. And he's like, oh, yeah, it's okay. It's casual, right? This is just Riemann relaxed fence building. Maybe this one, I don't know. Maybe we'll go and attach it right here. As long as it's attached somewhere in the little subinterval, Riemann is totally happy. He doesn't really care how wide these ribbons are either. He's like, oh yeah, no big deal. right? As long as we can kind of get this thing put up, we're fine. So looking at this story here, it looks like we're using some pretty interesting y values to decide where to attach this fence, right? So I'm using maybe that y value, maybe this y value, oh, maybe all the way down to that y value, and maybe this one. And then when I'm trying to figure out, like, well, where are these fence runs starting and stopping? Well, we got to start at 1, and he's like, I don't care. Stop the next one at 4, stop at 6, stop at 10, stop at 13. No big deal. And so he's very relaxed, and he says, you know, I think we can come up with a nice approximation for the area. How about this? We'll figure out how tall this ribbon is by going and finding out what f at 2 is. You know, just some random spot along the way. And we'll multiply by how wide this ribbon is. 4 minus 1, that looks like it's 3 wide. Next ribbon, well, we need a height. How about f at 5? Multiplied by, that one's only 2. And he's okay with that. And then the next one, how about f at 9 could be used to find the height, as long as it's somewhere along that ribbon. And, oh, that one's 4. And then one more ribbon. Oh, okay, f at 11, that's along the way, that'll work. And then that one is 3 wide. And that's his plan. He's like, yeah, not a big deal. Make them as wide as you want. Make them as narrow as you want. Just make sure that you're using some y value in the middle in order to find out how tall they should be. Okay, so that was me showing you with a specific example with some numbers that I can point to. Like, hey, look, 2, 5, 9, and 11 for the x's that we find the y's at. And fence posts that begin and end at 1, 4, 6, 10, and 13. Well, now let's go and talk about this kind of in general. So it's going to get a little kind of mathematical looking, right? A little theory looking. What if there are n of them? What if we don't know that there are 4, but what if there are n rectangles? Now remember the fence post issue. If there are n ribbons, that's like the pink fence runs here, we have to have one more fence post. So we're actually going to have, if we've got n rectangles, n plus 1 fence posts. Okay, here we go with some labels on this. Let's go and label in where we're going to start. I'm going to start right here, and I'm going to call that my beginning spot. Maybe I'll finish just like we did before. I'm going to finish here. That's my last fence post. I know there's supposed to be one more fence post than there are rectangles, but I kind of want to call this last x value x subscript n. And looking at the way we did this up above, right here was this transition where this last ribbon started. I'm going to call this like x n minus 1. And back at the beginning, I don't want to call this x1. I'm going to start counting like a computer scientist. I'll call it x subscript 0. And then I can say, okay, my first ribbon finishes at x1. My next ribbon here finishes at x2. So those are where the ribbons start and stop. Let me go and grab a ribbon so I can just copy it in here. Now I promise you it's going to look a little theory based, right? Riemann says, okay, that first ribbon goes from x0 to x1. So ribbon number 1 ends on x1. And he's like, look, attach it somewhere. And you're like, Riemann, where? Where do you want it attached? And he's like, look, I don't care. Just find some spot along the way, like maybe here, and then go and attach that ribbon. The x value that you attach it at, okay, that attachment point, we're going to call that x value, it's the x value for ribbon number 1, we're going to call it C1, some chosen x value along the way. All right, well, let's keep doing that for the rest of these ribbons. Okay, here goes another ribbon. Again, he doesn't really care how wide they are. He's just going to say, look, they're going to start at a starting point, finish at a finishing point. For ribbon number 2, it starts at x1, finishes at x2. And he says, lock it in somewhere along the way. Okay, same general plan as up above. but it's going to be all general stuff now. No specific numbers. Okay, I'm really just drawing the same picture as up above, but I want to keep this totally mathematically general. So the C's are going to be the locations where you go grab some X values in order to find Y values. They have to be along that partitioning of the X-axis. They have to be inside your ribbon. And then the last one's going to finish up. This will be, C subscript n. Actually, this C, yeah, it's the third one in from the right, but maybe by now I should be calling this Cn minus 1, right? And then the last one is Cn. And so the area, well, here's how he would write it. He says, well, there's probably a lot of them, so why don't we say this? The first ribbon, here's how tall it is. It's F at C1. And then you have to multiply that by how wide that first little fence run is. So I don't know, we need another color in here. Let's go green. So you go up to this first fence run and you say, okay, I got to measure this. From x0 to x1, how wide is this? What's the delta x? But the next delta x is different. So we might need some individual names for these. Why don't we call this delta x1? And this is delta x number 2. And so on until we get to the last ribbon where you can say, okay, final ribbon, the nth ribbon is delta, oops, let me fix that there, is delta xn, the nth width. Okay, so the first ribbon is F at C1 multiplied by delta x1. Then you add on the next ribbon. There could be a lot of these. So we're going to find the height of the ribbon by finding what the function's doing at C2. We'll just go and find the y value. And then we'll multiply that by the width, number 2. And you keep playing that game until you get to the end, until you get to the final ribbon. And by then, you'll be doing this for the nth time. And this is function figured out at Cn multiplied by width size n. Well, it's a pain to have to write that, right? To say this one plus dot, dot, dot until you get to the end. So sometimes we use that sigma notation from the math department and we say, all right, we're going to be doing some sum. Let me change my colors here. We're going to be doing a sum of these n terms. And so why don't we go and set up one of these little summation things, right? Greek letter sigma. That's going to add them all up. It's going to add up all these stories where we take a function figured out at some C, C1, then C2, then C3, then C4, and we're multiplying it by the width of each one times width x something or other. And it's going to be done for like with 1, with 2, with 3. So we have to come up with a counter. And the way the math people like to do this is they say, okay, look, how about K for counter? Because they don't know how to spell, right? So K for counter, we'll start off with rectangle number 1, and we'll go all the way up to rectangle number n. And so this would be C subscript K and delta x subscript K. And that says, all right, start off with K1. That's this term, right? So when K is 1 at the beginning, that'll be this term. And then do K2. That's that term. And keep going and going and going until you finally get to the last one, which will be n. So this top thing on the top tells you where to stop. Now you might also see math people say, okay, well we should tell people that we've taken this field and fenced it off, right? So you might see some official language in here where they say where, and then they'll show you how they've set in their fence posts. x0, x1, x2, dot, 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 all the way out to xn. Okay, so those are your fence posts, is a partition of that area on the number line from A out to B. Okay, well that purple stuff's pretty technical talk. Let's just go back to a nice simple picture. That's like saying, okay, we're starting here, we're finishing there, and we're just parting the field by shoving some fence posts in. That's all that that's saying. Okay, where you shove the fence posts in, really relaxed wherever you want, and that is us trying to find the area. Now, at first glance, when I look at this, I gotta say, I think it's maybe worse than yesterday in terms of being accurate. Like now, not only is it these big silly rectangles, but they're not even all the same size, right? So who knows whether the errors here are bigger or smaller. It could easily be worse. But then Riemann says, okay, I was just getting it ready, just kind of laying it all down in terms of the notation. Now let's make it right. Let's actually come up with the perfect area. The plan is to deploy what we saw last day back here, where we said, wait, this story gets better when the number of little Riemann ribbons goes up and up and up and up. Even if they're sloppily built like this, even if some are a little wider and some are a little narrower. So this next page, we're only going to do this once. I am not going to ask you to reproduce this, but I want to show you a whole bunch of different ways that this can be written down. Okay, trying to find the area under the curve. So it's an approximation. It is not perfect if I say, oh, well, let's just do ribbon 1 plus ribbon 2 plus ribbon 3 all the way out to ribbon N. These could be really wide ribbons. This might not be a very good approximation. But if you want to make it better, if you want to say, no, I want this to be perfect, then what you need to do is a limit. So you say, okay, let's do a limit. Let's make the distance from one fence post to the next to get smaller and smaller and smaller. And the notation for that in the math world is you go like this. Double bars, P for partition, heading to 0. And that means just get those fence posts more and more together, which means you got to go to the hardware store and buy more and more of them. So we're going to do a limit of this sum. So on the first day we said, I don't know, just go and add up some rectangles, right? That's this blue stuff. But if we go and add up more and more and more rectangles, making the fence posts closer and closer and closer, this becomes perfect. So I'm changing this to an actual equal sign here now. Okay, well, I don't want to have to write all that blue stuff out like that. That's a hassle. So, all right, let's get lazy like a math person here. Partition's heading to 0. In other words, if you were to draw this like in the field, if you were to go there and say, what does that mean? That limit as P goes to 0. It means do this. Fence post, fence post, fence post, fence post. Just like this. Keep going until there's basically no distance between the fence posts. Just more and more and more of these fence posts. Okay, well, fancier notation here. Instead of having to write A1 plus A2 plus A3, let's do that sigma notation thing. Let's go and say, hey, we're going to do a sum. That is the worst looking sigma I think I've ever drawn in my life. Try that again. Marginally better. We're going to sum up all of these A's. A1, A2, A3. So how about I just call it like AK, and then the K's will begin at 1 and finish at N. That's the same way as talking about the stuff inside those green brackets. Okay. Still talking about different ways to write this. Now we're only going to do this once, so don't panic. It's not a big deal. All right, that says lots of fence posts, please. Now, how do you find the area of each one of those ribbons? Well, when you're trying to find those areas, we're summing all these up. K goes from 1 to N. I have to take the Y value for that kth ribbon and multiply it by the delta x for that kth ribbon. Okay, keep going. More ways to write this. We're getting close though. There are only 3 more rows left. We could say we're doing a limit as the spacing between fence posts goes to 0. If I wanted to find y values for those ribbons, I would use the function. So let's tell people that. This y of k, we're going to take the function and go and put in one of those x values along the way, ck, right? Some x value inside that ribbon, and then multiply that by the width. Now, another way to write that, and I'm going to be honest, I'm going to steal this. I'm going to write the same thing. So I'm going to cheat right now. I don't want to write that again, so I'm going to just write it like this. Say, okay, yeah, I've got that. And a different way to say, oh yeah, the limit, as that partition goes to 0, people also sometimes say it like this. They say, let's do a limit as the number of fence posts goes to infinity. Same thing. So if little n was the number of fence posts, yep, go to the hardware store and buy a lot of them. So this is the exact same idea as that one. It's just a different way to say it. More and more fence posts, closer and closer together. Now, getting fancy. What we could do is we could say we're trying to do a limit as the number of fence posts goes to infinity. We want this to be perfect. And instead of writing that sigma, because I don't know about you, but I am horrible at writing them, why don't we just say, hey, we're going to do a sum. We could stretch out the letter s if you want. And we're going to be summing up some height, figured out at some spot along the way, multiplied by the width. And that would actually perfectly find the area. Okay, it's going to be a perfect calculation, but we have to do an infinite number of fence posts. So this is called an integral. When you see that, I want you to think, hey, it's perfect. It has an infinite number of fence posts, infinitely thin widths, and it's going to do a perfect job of finding out what that area is. Let's tear it apart for a minute. Okay, there are different bits and pieces to it. For starters, this big stretched S is there. It actually is the letter S that's been stretched out. And you're going to see two numbers on it, right? An A and a B. That's actually going to be where the very first and the very last fence post goes. So we'll talk about those as being the lower limit and the upper limit. Where do we begin fencing this field off, and where should we stop? Then inside there, you're going to see this. You're going to see f of x multiplied by dx. Super small, thin little width. You should be thinking, because this is true, that this is talking about the height of each one of those ribbons, and there are an infinite number of them. And this is talking about that super thin width, infinitely thin, the width of every one of those ribbons. The letter x in this picture here is what we call the dummy variable. Not that it's stupid, but because it could be any letter you want in the alphabet. It doesn't actually matter. Okay, so that's this thing and that thing. As long as they're the same, then we're okay. The whole thing is called an integral. But if you want to talk about just the stuff inside the integral, like sometimes we talk about stuff inside roots, stuff inside radicals, and we say, oh, the stuff inside is called the radicand. Well, the stuff inside is called the integrand. Just some vocabulary. That way if somebody says, hey, well, let's just look at the integrand for a minute, you know where they're looking, right? They're actually looking at the stuff inside the integral symbol. So, quick little summary of what we've seen, because it looks intimidating, and it doesn't need to be. So a Riemann sum is really just a sum of rectangles. In fact, can I put in here just a little casual language? It's a relaxed sum of rectangles. Probably not even perfect. But a definite integral is it's going to be perfect. Okay, it's a limit. I want you to think perfect. Of a Riemann sum. I don't think my grammar totally makes sense there. But it's the limit of a Riemann sum. It's going to be perfect. And it's going to be perfect because every interval, every width, every delta x goes to 0. Another way to say that, you're going to have an infinite number of ribbons inside this story. So all you need to know right now is that that symbol means, oh, do it perfectly. Let's try out just a couple of examples. The first one, it looks way more confusing than it deserves to be. It's just, I wanted to show you one that's similar to the homework in the textbook, so you can see what this is all talking about here. So it says, express the following Riemann sum limit as an integral. So I can see that partition going to 0, meaning that it's going to be perfect, right? That's all that tells me. It says, oh yeah, we're taking this to the extreme. We're going to do a perfect calculation of the area. So why not write this in a much nicer way? It looks like this stuff right here, this is somebody figuring out the function's height at some randomly chosen value called z inside each interval. So I would look at it and go, okay, here we go. Let's write this as an integral. This is going to be an integral. We need a starting and stopping number, and they've told me right here, okay, yep, it's this partition. There's the start. There's the stop. So yeah, we'll just go from -8 to 11. Thank you very much. And then I'm going to put the function in. I'm going to say, well, it looks like the function they're playing with is 5x squared minus 3 all over x. And then you write dx for the width of the integral. Right now, I don't even know how to do that, but I know that it would be perfect if I could. It would be perfectly finding the area under that graph from -8 all the way out to 11. Okay, well, let's just use the concept of perfection and your knowledge of finding areas to see if we can calculate some of these just based on our grade 9 knowledge. So use your concept of area, like grade 9, grade 10 skills to find each of these integrals. So this story, when I look at it, tells me that we're playing with this graph, y equals 2x plus 1. We're apparently trying to find the area underneath it, starting at 1, finishing at 3, and they want to do an absolutely perfect job of finding the area in here, right? That's the request. Could you do this perfectly? And my answer is, well, not with calculus just yet, but maybe based on my knowledge just of shapes. So I'd probably look at it and say, well, why don't we break this up maybe into like a rectangle and a triangle? And if this is really supposed to be finding the area, the perfect area under that curve, well, maybe I can just go over here and doodle. I'm going to have 1/2, base of 2 for the triangle, height of 1, 2, 3, 4. Okay, the triangle there is 4. And then length times width for that rectangle, it is 2 wide, it's 3 tall. Okay, that's 6. Oh, okay, hey, here's my answer. This is a perfect calculation of the area under that graph, and it's going to be 10. Done. This next one, I sort of recognize that function, starting to recognize it. Now that's a circle. It's a circle of radius 5. Okay, so that's this thing right here. Okay, that's going to be y is equal to square root of 25 minus x squared, at least a half circle anyways. And they're saying, would you mind going from -5 to 5? And this tells me that they're doing it perfectly. Somehow, maybe with some calculus skills, they are absolutely perfectly finding the area of that picture underneath that graph. Well, I don't know how to do that with calculus. But what I do know how to do is find that just as a shape, right? I could sit there and go, okay, look, it's half of a circle. So it's going to be half of pi r squared. So it's half of pi times 5 squared. Okay, I'm done. I don't know how to do this with any calculus, but just looking at the shape, it's going to have to be 25 over 2, so it's half, multiplied by pi. No idea how to do that with calculus just yet. This one, just a constant function, just y equals 5. Pretty boring graph. And they're saying, hey, would you mind integrating this thing? Would you mind doing this definite integral starting at -2 and finishing at 8? So I can see what they're saying here, right? This is a perfect Riemann sum. So Riemann's coming in with an infinite number of fence posts, and he's going to perfectly find that area. Well, one day I'll learn how to do that with some calculus, but right now I can just do this with some simple math skills. Looks like a rectangle. Looks like it's going to be 5 tall and 10 wide. Oh, okay, so here's the answer to your calculus question, 50. And for now, that's all I'm trying to do. You know, I guess we could kind of come up with a general answer to this last one, right? We've got this constant value, right? Looking at the story here, this c, right? Like y equals c. So what happened? Well, if we were to come up with a formula for this, I guess it's c tall, and then how wide is that rectangle? It goes from a out to b, so b minus a, right? That would actually be 5 times the 10, right? Later on, we'll see much better ways to do that with calculus. Next issue, we're going to talk about something that I'm just going to casually refer to as net area. Okay, there's no real nice way to talk about this, but we're going to go with net area for now. If you've got an integral, like let's say this one here, that goes from 0 to 6 for that f of x. If I try to do that integral, if I'm playing around with a graph that during the time that I'm looking at it, it's always positive, right? So from 0 to 6, yeah, I haven't gone into the negatives yet. Things are good. If your graph is nothing but positive, then when you go to do that integral, when you integrate from a to b, when you integrate your function, that's what we call it, that's the verb, you are truly finding the area. You would absolutely find the area. So we would actually find the area of this shape right here, and the area of that shape is actually a 9, right? Just doing work with triangles, 1/2 base times height, great. So sure, that symbol means go and find the area, but that's if the function's positive. If the function that you're playing with is negative during the time that you're watching it. So for example, what if I tried integrating that same curve over there, same f of x, but from 6 to 10? So now I'm looking at this section right here. When I go to find that integral, because it's negative, I'm going to do something kind of neat. It's actually really helpful for physics. If I integrate from a to b, my f of x dx, if I'm in the negatives all the time, then I'm going to get the negative of the area. It's going to give me a negative number. So the calculus is going to look and say, hey, did you notice that this triangle is hanging down underneath that x-axis? And that little triangle has an area of 4. You know, if I had to go and paint it, if I went to the hardware store and I'm like, hey, what's the area here? The area is 4. But the answer to this calculus question is actually going to be -4. So we might say, oh yeah, well the net area is 4. Kind of like speed and velocity, right? Removing any minus signs. Where it gets interesting is what if it's both? What if your graph is actually doing both of those things while you're trying to look at it? Then you have to be super careful. So for example, same graph, but what if I try to do an integral from 0 to 10 for f of x dx? What's that going to say? Well, there's a time when this graph is above the x-axis up here, and then it transitions to being below the x-axis for the last part of the story. If I go to the hardware store to buy paint, I need to buy 9 units of paint for that, and I need to buy 4 units of paint in here. So areas technically are never negative, right? So you're going to go paint this. The area is going to be 9. You're going to go paint this. The area for that little blue shape there is 4. Like, you have to buy paint. It's going to be 4. But if I actually go and find this calculus story, it ends up being 9 minus 4. It lets the two fight each other, and it would actually say the answer is 5. Okay, so if you've got both up and down, then the integral, this thing, let's get our colors right here, we'll stay green. Then the integral of your function, it's going to equal the area above minus any area below. That's actually super handy for physics. So how do you want to call that, right? Do you say that the area is 5? Well, we might say that the net area is 5. Right? So areas really can't be negative, but we'll use this little phrase net area whenever we want to. Final one. You know, in a short time, we'll be able to actually do these integrals. We'll have some skills to do it. But for now, we're just trying to think about what they mean. So what if you're given this information here? Somebody has said to you, hey, I know you don't know how to do this yet, but let me tell you that that integral actually works out to be 8/3. And it's figuring out this area right here in black. It's above the x-axis, so it's a nice positive area, and it ends up being 8/3. Okay, 2 2/3. If somebody says to you, well, what do you think about this answer from -2 to 2? So they're trying to do all of this black area. That's a nice even function. And so I think what's going to happen here is you're going to get 8/3 of area in here, and you're going to get 8/3 of area in there. So this answer is actually going to be 16/3. Well, what about this one? This one's tougher. But you know, maybe what I could do is I could kind of think about this as being part of a big rectangle, and then we're subtracting off a little bit of white space. That's what this is saying here, right? If I go, okay, parabola -4, and if I'm integrating, maybe I can figure out how much black area there is there. The area for this big green rectangle, that's pretty easy. That's just going to end up being, what is that? 2 times 4, that area is equal to 8. And it looks like this area in here is 8/3. It's the same shape. Sorry, oh, wrong spot. Try that again. Let me clean that up. Jumping around here. There we go. All right, a do-over. So this area in here is just like the shape they were telling me about right there. That's 8/3. Okay, so that black area, it's going to be 8 minus 8/3. So I could sit here and go, okay, 8 minus 8/3. That's like 24/3 minus 8/3. So I'm going to call that 16/3. But there's a catch. This area is actually hanging down underneath the x-axis, right? Like, take a look. The x-axis is right here. So that area that's down there, the calculus people, they're going to say, oh, well, let's call that -16/3. And we're going to do a lot more work with that, trying to figure out, well, should we call this answer, this perfect answer for the area, should we call it positive or should we call it negative? We're going to sort all of that out in the next little while. But that one would actually be called -16/3. Okay, so we're going to stop there. That's enough for today. And then next day, we're going to look at just more plans for these definite integrals, these perfect areas. We're going to look at some rules that you can count on to help you out. And then eventually we'll come up with a plan where we can do these perfectly with some calculus.